everyone. Welcome to another episode of AI Research Today. We are going to pick up another episode with a paper named Spiral, Symbolic LLM Planning via Grounded and Reflective Search. I'm your host, Aaron. Have a background in AI research, consulting, software development, the full plethora of weird computer stuff. I'll, as usual, put this paper in the episode description. The reason I chose the paper was because it involves MCTS, which is something we've talked about in a couple of previous episodes, including optimizing mathematical reasoning chains using MCTS and some other agent MCTS applications. We talked about like a meta learning sort of thing in a previous episode. The paper itself is pretty neat. It's applying a sort of augmented MCTS into the LLM inference environment, I should say. So this isn't necessarily like you train a model using this method and then you would deploy it. This is more of that sort of trend where we're allocating compute more towards test time versus inference. So it's a heavier test time compute, but again, doesn't require large RL training instances to fine-tune some model for an app benchmark. So the paper itself targets some planning benchmarks, so agent planning benchmarks. One of them is called Task Bench, but basically the request is to come up with a plan of what you're going to do to solve a particular agentic task. And these tasks would be sort of like everyday things that someone might do in a web portal. And if your plan closely matches the plan using sort of like a string match sort of setup, including syntax and invocation rules and things like that, then you're judged to have generated a complete and correct plan. Obviously, there is a lot of research into agentic planning. Some of the more common agentic prompting techniques like React, and there are a few plan variants where you have it generate an entire plan up front, have been shown to improve agentic performance. And so this is sort of a proposal for a way to come up with a better plan than just relying on a sort of one-shot inference pattern from an LLM as part of a prompting technique. So they provide 3 or 4 different improvements to agentic planning. One of them is what they call a proposer agent. And then they have a simulator agent and a critic agent. And so I'll get into this a bit more, but just sort of like going through the abstract here, the proposer agent proposes an action, the simulator agent predicts an outcome, the critic provides a reward, and you sort of do that to build up your tree. And then you choose the best path from the tree as your answer, basically. So that's sort of their contribution, is this sort of augmented MCTS. Just to give a little bit of some preliminary background covering what they covered in the paper, So the typical sequential decision making process is a Markov decision process where we have the environment's defined via some tuple of state action pairs, as well as like a transition function and a reward function, where our state space is some set of states. So this could just be like database states or whatever your environment states are going to be. And then some action space. In this case, the action space consists of a set of tool calls, as well as a final call, like terminal finished or whatever, and that signifies that the agent's done. And then you have some transition function that takes the environment and the action and gives you some new state. And your policy, of course, is what makes the decision for what action to take given the current state of the environment. They introduce so in a normal RL situation, your transition function is either stochastic or deterministic, but nonetheless dictated by the environment. It's not something you necessarily know a priori. The transition function just sort of gives you a new environment state when you take an action. So like you're walking down a hallway, you say, I'm going to take a left. And now your environment is you've taken a left and you have to either choose to go straight or go right. So the environment is sort of predetermined, and that's what's transitioning you after you take an action. They approximate this transition, however, with what they call a world model, which generates a plausible observation based on the state and the action tuple. And your reward function, of course, is just something that gives you some reward based on the state and action. And then your overall objective is to find a policy that generates a sequence of actions that maximizes your expectation of your cumulative reward. So that's just the standard RL setup. MCTS is sort of a follow-on way of solving a problem like this. I guess it's sort of like a dynamic programming sort of variant. But you're basically trying to find or assign a value to every state in the environment. And there can, of course, be a ton of states because in certain environments, there can be almost infinite actions you can take. And so the state space dimensionality explodes, which is why, like in the AlphaGo setup, for example, they used MCTS, but they use also a value function where they're predicting the value of a certain state rather than like rolling it out to the end, just because there's so many potential things you have to deal with and like how large your state space is. So, but Monte Carlo Tree Search is basically just building up a tree from a root. So the root would be the start of your environment's problem. Like you need to purchase a t-shirt on Amazon as long as it's within the budget I have in my Venmo account. And so to do that as a person, you'd have to go in Venmo, check your balance, say that, I only have $30 in my Venmo account. Now I'll go on Amazon, have to find t-shirts that are under $30 and then purchase one of them. So in this case, the root would be like purchase a t-shirt using my available Venmo balance. And then you sort of start traversing this tree. So from the root, you choose a node, and then you traverse the tree until you get to a spot that you haven't seen before. How do you traverse the tree? You use something called an upper confidence bound. This is just a fairly simplistic formula that is a combination of factors. So it's proportional to the number of times a node has been visited before, as well as the value or the reward that's been allocated to that node. So you can balance exploration, exploitation using a weighting constant in the UCT formula. But basically you have this UCT formula that you start at the root of your tree, you choose nodes or actions based on UCT, or that results in new states, and you traverse the tree until you get to a node that's a leaf node, and that means that it hasn't been expanded yet, meaning that there are no children attached to it, and so that's when this expansion phase starts. So at that point, you take a new unexplored action, and then from the resulting state, you do a rollout, which is just in traditional MCTS, a random rollout. So you just randomly choose actions and states from there until you reach a terminal state. And then once you've reached the terminal state, you have some reward, like, did I complete it successfully or not? And then you back propagate that reward up the tree to the ancestor nodes chosen to get to the terminal state using a fairly simplistic back propagation formula that sort of just weights the distance of the node from the end of the tree and allocates some amount of the reward to each node in the tree. Okay. So that is MCTS. How do they use that here? The problem is, MCTS is pretty sparse rewards, so you don't see a reward till you get to the very end of the chain. And the state space is very large, so it can be difficult to ensure that you explore enough to find a good result without sort of dying on the branch of infinite dimensions. And so they come up with this spiral proposal where you use the UCT formula still. So it's the same UCT formula to traverse from the root to the leaf that you would in a standard MCTS. But once you get to the leaf, you do sort of like a one-step plan iteration. So the planner, these are all the same LLM, by the way. They're just sort of, you make 3 calls to the same LLM with different templates to get each of these different outcomes. So you give the LLM this planner template, and that tells it to choose an action. So like, these are your available actions. This is your interaction history. Choose an action. So the planner chooses an action. Let's say open up the Venmo app. The simulator, and to do that, it provides some code snippet, right? Like, this is the Venmo app API code, and this is how I want to call it. The simulator is what allows them to provide a more dense reward signal than just waiting until the end of the rollout. So the simulator provides a predicted result. So the planner, it takes the planner's input, it takes the state and whatever else you have, API documentation, whatever, and it says, okay, I predict that given this API call with this parameter set, this is going to be the outcome. Either like it works or it doesn't, or something along those lines. And then the third dimension of this spiral algorithm is the critic. And the critic provides a reward at each step of this rollout process. Rather, you're not just waiting to the end of the rollout at a terminal state. You're getting a reward at each node, and the reward is assigned by the critic. And it's a combination of 2 things. So this actually becomes a hyperparameter in their algorithm they call alpha. But your reward at time step T is a linear combination of what they call R base and then row pref. So row pref is the actual like structured output float from this planning critic. So, I took the predicted outcome, I took everything else, I took the initial task, and I think this is a really good or a really bad action to take. And it provides some kind of float structured output, and that's what they call row. And then they have R base. Now, R base, I'll be honest, I had to track down what that is because it is not explicitly defined in the paper other than through some words. So there's no like mathematical definition. They do release their GitHub code, which I went through, and I'll link in the episode description as well. But it appears to me, and someone correct me if I'm wrong, because I had to infer this from reading through their Git repository, but rbase is basically like a heuristic. So rbase is like a regex syntax checker. So, using the API docs, was the code generated syntactically valid? And I guess you could edit any other sort of standard heuristics you want to in there. So it's sort of like standard heuristic checker plus like an LLM reward based on the historic conversation, the simulator, the planner, etc. So you end up getting your reward for the node is this combination of two different things, rbase and row. And those are multiplied by alpha, which is just like a weighting coefficient, like what percent you want to weight the heuristic versus the critic's reward. So the overall algorithm here follows this approach. So we start at the root, we iterate until we get to a leaf node. So if this is our first iteration, it'll immediately be a leaf. If not, then we'll use UCT to traverse the tree until we reach a leaf. At the leaf, we generate an action with the planner. We generate an outcome prediction with the simulator. And we use the critic to assign a reward and then add that reward to the heuristic reward and then immediately backpropagate. So we're running a backpropagation at each node in the tree until we reach the final node. And the final node, the critic will be asked to, does this look like a successful trajectory? Yes or no. So it can provide like a really high weight or a really low weight. And then that's backpropagated. If they go through some pseudocode later in their paper, and they do state that if you're doing a rollout, like using UCT or whatever, and you reach an existing terminal state, you assign it a low reward, like -1 or something, and then propagate that back up. I guess with the intent that you want to explore the tree broadly. I guess, the critic's assignment of the reward to positive versus negative trajectories, you would still maintain that differential with adding a negative reward to disincentivize traversing to a terminal state. Although the more you do it, the less of a difference there'd be between those terminal states, like the positive and negative ones. And another thing to keep in mind here is there's no actual code execution going on here. So this isn't like you take an action and what the environment's actual response is. So there's no terminal reward defined by the environment. This is all sort of like just planning. So this is just generating a plan. So there's not like any hard result from any code environment that's being used here. So everything just sort of has to be inferred by these LLMs based on the description of the environment and the tools at hand, etc. But they run this algorithm for 50 steps. And then at that point, you have a somewhat built out MCTS tree. You have rewards for certain nodes. And then you just choose the trajectory with the highest reward. And then that becomes the answer for like your benchmark, in this case, task bench, where you provide a plan, like this is what I plan to do. And the benchmark says, okay, that's a good plan or a bad plan. So they test this on a few different models. They tested on Llama 70B, Llama 417B, 514B, Quinn 2572B, DeepSeek 2.5, and they compare a few. They compare Hugging Face APIs, daily life APIs. Again, sort of like planning agentic planning benchmarks. And they provide some comparison to chain of thought, prompt planning versus their spiral technique. And the spiral technique comes out on top. I think some things to note, they do perform some ablation study with various values of alpha, and they show that there's a positive uplift from the critic, the LLM critic versus the heuristic. The repository, they do release their code, asterisk, because the repository is a little weird. Like if you go into the main branch, there's really nothing on it. There's like a environment file and a requirements file and a README. There is a dev branch, but the dev branch seems to differ significantly from the code that's implemented in the paper. So the dev branch is only using the heuristic R base. So there's no alpha or critic LLM in the GitHub dev branch, which is the only branch with any code on it. So in the dev branch, what they do is they use the planner, they use the simulator, but then the reward at a node is just taken as sort of like a regex string parsing. Like, was this API call in line with the API call the documentation says? Like, does it match parameters, etc.? So there's no real like critic reflection or, again, weighting by alpha or anything. Obviously, they quote that they did use the critic and they did ablations on it. So I assume that they probably either retroactively pulled the code off the main branch or decided to keep it internal to this paper was out of IBM and Vanderbilt, so probably IBM. So yeah, it would be difficult to reproduce the results. They call out their run environment was an 8-node A100 cluster, and they do provide in the end of the paper the pseudocode as well as the prompt templates they use for the planner, the simulator, and the critic. So yeah, I don't really know what to make of the Git repository. It's a little strange. I think overall the paper, I've said it before, I like MCTS. I think one challenge they didn't really address in the paper that would be interesting to look into is the accuracy of the critic. Because I've done stuff like this in production. So, for example, one use case we did, we had an LLM users were talking to, and users had some profile characteristics, and we wanted the LLM to condition itself and sort of choose responses or categories of responses based on the user's profile. And we set this up with a contextual bandit. And so we had to create training examples, right? So like, here's our historic data and a historic conversation. At time step T, the model decided to intervene and choose a different response than the baseline response. And so then you have to say, like, was that outcome positive or negative based on that choice? And so we used an LLM as a judge to assign a value. So then, we have like a reward based on where the next 10 back and forth's good or bad or whatever. And so we had this sort of structured output float value from an LLM, and that becomes your RL training signal. Like you had your input, train, intervention, decision, and then your reward. And so you can update your context bandit based on that training example. But what we found in practice was it's very difficult to get the LLM to give good results as a critic. Obviously here they do the ablation, so they show that the critic's providing some positive uplift. But it would be interesting to address how to train the critic itself. So if you could sort of like fine tune the critic on the benchmark somehow or something like that, that would be an interesting angle to investigate. Also, obviously, this is going to use a bunch of tokens because you're building an MCTS tree during inference. So likely higher cost from an academic standpoint. It probably makes sense because you're going to beat some of these benchmarks that are just asking for a plan and don't necessarily care about how many tokens you use to get there. But from a live inference context, probably going to be pretty high latency and eat up a lot of tokens, so it'd be fairly expensive. And yeah, the other thing, of course, is that this is all being done. I don't want to sound negative, like all being done in the model's imagination. But it is kind of, because there's no actual feedback from the environment during the building or execution of this plan. So it would be interesting to kind of extend this into a live environment as sort of a way to better traverse a tree. Like we discussed the app world benchmark in an earlier episode. Applying an MCTS tree like that could be interesting. But nonetheless, I think it's a pretty positive research contribution. I don't know. I've had a recent affinity for MCTS trees. I think there's just so many situations across such a diverse range of problem sets where they seem to be so effective, and they're fairly simple. There's not necessarily anything complex going on for at least the base MCTS algorithm. So hopefully some cool work builds off of this. I think there's some directions you could take it for sure. I would love if they updated their Git repository a little bit, so it's a little bit more intuitive. But yeah, that's sort of takes us to the end of the paper. I think it's yet another interesting way people are improving the performance of agentic LLM applications on these benchmarks, and I'll continue to keep an eye out for new papers that pop up. If you have any suggestions of papers you'd like me to cover, feel free to email them to Aaron, Aaron, at architect-ai.com, arkitekt-ai.com. Or I think like the podcast thing, have a little like reach out to the author or whatever, if you want to connect with me that way. But yeah, other than that, appreciate you listening and hope you have a great rest of your week.